Right. So yeah, as Steven introduced us, we are PhotoML. We're basically working with a startup to automate the process of image culling. And I think Dave is going to start off with the slides.
Yep, I am. Could you go on the next slide? Okay, so hey everyone, my name is Dev, and I'm super pumped to present what we've been up to over the course of the last few months. Gursimar, Chris, and myself will be speaking to our collaboration with PhotoML or PhotograFirst. So prior to September 2022, the founders of PhotoML reached out to UTMIST with their startup idea of automatic photo culling. And this project was really unique because it was a collaboration with the startup. And PhotoML provided us with computing funds, data sets, and domain-specific advice through consulting with professional photographers as we developed the machine learning solution. Next slide. Now I'm going to speak a bit to the project scope and sort of the overall goal of the entire project. The main problem was that photographers typically take a few thousand images in any given shoot, but only select a few hundred for the final product. And this process of cutting down is known as culling. And culling is a long and tedious process through which photographers select the best subset of images from a larger group of images. And our goal was to make the machine learning model personalized, as each photographer culls differently. Some may have a preference for certain angles or color composition, while others do not. And we wanted to personalize this process of culling by creating an algorithm that could learn how each photographer culls images, then being able to perform culling in a way that reflects their artistic style. And for this project, we set our scope to culling wedding photo shoot. Next slide. And here's a rough demo of what culling actually looks like. So there's a large batch of images, as you can see on your left, and from that batch, a small subset of images are selected, and the rest are culled based on several criteria. And throughout this presentation, we'll be speaking to what this criteria actually is. Next slide. And for our approach, we only knew what kind of output we wanted our algorithm to give. So we sort of worked backward from there. The algorithm sorts images into three different buckets: the certain bucket, the uncertain bucket, and the cull bucket. The certain bucket contains the images that the photographer will choose like 100% for sure. And the uncertain bucket has images that may be discarded or may be chosen depending on what the photographer wants. And the cull bucket contains images that will be discarded. And now I'm going to hand it off to Gursimar to talk about our duplication detection model.
Right. So we started off with the duplicate detection model. It was one of our submodels. And we very quickly realized that this was a really necessary step of pre-processing, because every photographer would take like 10 or 20 images of the same scene in one go. And they would just continue snapping those images while the subjects in the photo are just moving slightly, maybe closing their eyes and opening them. And they do that to ensure that there's at least one or two images that they can select where everyone's eyes are open and there's no motion blurring. So when we take in this entire data set of 1,000 images, we need to be able to identify these duplicate groups, because otherwise, if we build a classification algorithm that works really well, it may just look at sets of very similar images and think, okay, well, this image is good, we should select this. And oh, here's another image that looks exactly like the first one, so let's select this as well. And so our final output would end up just being a bunch of images that look very similar to each other, which is why duplicate detection was a really essential pre-processing step. So we start off by taking the entire data set of images and we split it into different duplicate groups, and we pass each of those groups into the rest of the culling algorithm. And then we select the best images from each group to be in the final product. And our approach to duplicate detection looks something like that. So we essentially start off by extracting features from MobileNet v3. And later in the presentation, we're going to visualize these features using this sort of similarity matrix. And we basically use those similarity matrices at each different layer in the MobileNet features when we extracted those features to determine which layer we should use to perform duplicate detection. And after that, we use PCA for dimensionality reduction, because, you know, we had about 1,000 images in each incoming data set, and each one had like 47,000 dimensional vectors, and it wasn't really feasible to do clustering or anything of that sort on that many dimensions. So we first did PCA to reduce the dimensionality of the data, and then we used approximate nearest neighbors to estimate where the duplicate groups lie. based on which vectors were close to each other. So I'm sure you're wondering, why not image clustering? The main problem with that is that we did not know the predetermined number of image clusters, because when we get an image data set, we don't know how many duplicate groups will be present in it, nor do we know the number of images in each cluster. So in this case, it was much easier to define some sort of similarity metric between different images, and then estimate a threshold value for that metric. So if two images had similarities above the threshold, we would consider them as part of the same duplicate group. So in this slide, we essentially show what our different submodels were and what was the rationale behind each submodel. So photographers would typically look out for many different features when they're doing image culling. For example, the emotion of the people in the frame, whether their eyes are open or closed, the color composition of the image, which includes things like lighting and etc., and as well as the use of the space in each frame. So we wanted to account for each of these features by having a submodel that extracted those features that the photographer would look out for. And then we used those features to essentially somehow make a prediction about which class an image should belong to.
Yeah, so now I'm going to go over more in detail on what our approach to the submodels were. So in this diagram, it's just a refinement of what we just showed in the previous slides, but we're just essentially splitting the culling algorithm into its actual components. So in the diagram, the green shows our pre-trained models and the blue shows the models we trained. And when the images are inputted, they first go into the duplicate detection model to carry out the pre-processing. And then we filter it out into however many n duplicate groups there are. And then for each of these duplicate groups, they're passed into our four models on closed eye detection, emotion detection, neural style extraction, and semantic segmentation, which we'll further explain in the next slides. Then all of these detection models and the results are combined into one ensembling model, which result in the certain bucket, the uncertain bucket, and the cull bucket that was explained earlier. Next slide, please. And then, so I'm just going to go over the emotion detection approach that we use. So once we take in an image of a lot of faces and their people, for example, in our scenario, if we see a photo with wedding images and people participating in that wedding, through our face detector system, we detect any sort of faces that appear in the image. And in this slide here, they are showed by green boxes. And then we extract all these faces using an open source library called FaceNet PyTorch, which uses the MT-CNN backbone for detecting and drawing bounding boxes around the faces, which are again showed in green here. And then after that, that's sent into our emotion recognition model. And then so these individual faces are just cropped by themselves without their bodies. And then they're passed through our custom emotion recognition model trained on a large open source data set from Kaggle. And if you look closely on the lower left image here, for each and one of these faces, we give a percentage representing the emotion that is being portrayed by the faces. So yeah, next slide, please. And then now I'm going to go over how the closed eye detection sort of works in our algorithm. So given those faces again, we take a look at the eyes themselves and we extract facial landmarks using the dlib library, particularly the 6 landmarks for eyes indicated from P1 to P6 in the slides. So with these 6 landmarks, we calculate the eye aspect ratio based on the formula shown on the slide, which the basic intuition on this formula is that we take the norm or the distance between 0.2 and 0.6, and then add that with the norm of P3 and P5, and then divide that over the double of twice the norm of the P1 and P4. So the intuition behind this ratio is basically that the higher the aspect ratio, the wider the eyes are open. So this is how we kind of determine if the eyes are closed or not. And then after that, we get the result of the aspect ratio. We pass this number, the output of the year formula, to the binary classification models. Next slide, please. And then in terms of our style extraction, we first deal with the image at hand, and then we flatten the image into a long vector, which discards any essential information about the structure. And this is just done so that we can only focus our algorithm in terms of the style, which would mostly be centered on color. And then after that, after we get that long vector, we multiply the vector with the transpose of itself. And then each element in the resulting matrix, or the diagonal matrix, is basically the dot product of a color channel with another color channel. And this represents the similarity of those two color channels, which is basically just the style of the image, which is how we extract the style from the initial image that we received. And then the same process can also be done with image activations after passing through layers of a pre-trained network like VGG or ResNet, and this encodes for more advanced stylistic features like texture, etc. Thank you. Next slide.
Right, so then we have semantic segmentation. This was also done using a pre-trained MobileNet v3, and it was pre-trained on, I think it was the ADE 20K dataset from MIT. And yeah, there isn't that much to explain here. It was just regular semantic segmentation. So now I'm sure a lot of you are wondering why the submodel approach. And the main reason is that the difference between culled images and selected images is very minor. And it's a very nuanced process of selection. And if we just simply allowed a network to classify images based on features that it learns by itself, then the results would not be as good, because learned features can be very arbitrary and they may not be helpful when the difference between our classification groups is very minute. So that's why we felt it was important to predetermine these features and then select them out. And also another advantage is that it's very easy to add or remove submodels based on what photographers like, and just the fact that we have a very modular structure, which allows us to just add new submodels if we feel like it. And it's also more robust because ensembling prevents predictions from being overly dependent on the outputs of a single submodel. And for this reason, we prioritize reducing the compute time of each individual submodel rather than having more accurate models, because we realized that having models with maybe a 2 or 3% accuracy increase was not really worth it, since we had 4 models that we were ensembling over. So it was just more important to have computationally efficient models. That's why you would notice that we use MobileNet in at least 2 places above. And for model training, we had 2 main stages in model training. Firstly, we passed images through the submodels, and we basically just passed the entire data set through the submodels and obtained and stored these output activations. And then we unified the structure of all of the output activations so that we could pass it in through the ensembling model. And the ensembling model essentially serves to estimate the importances of each of the features extracted from each submodel. And it basically just estimates how important it is to that particular photographer, say the use of the frame or the emotion of the people in the image. So it's specific to each photographer, and the individual stylistic preferences are encoded by the weights of this model. And here's a little demo of what the output looks like. So this is the similarity matrix that I was talking about earlier. And this essentially, each sort of square in the similarity matrix represents the dot product between the features of an image and another image. And you would notice that along the diagonal, we have these really bright squares because that's just the dot product of the features of an image with itself, which is obviously going to be very high because they're the exact same image. But we also see these the emergence of these sort of sub-squares, which are these like 3x3 squares. And we see that those are also much brighter and stand out from the rest of the matrix. And that's because those represent the similarity between images and other images in the same duplicate group. And this is essentially how we visualize the outputs of the MobileNet v3. And layers that had more distinct squares were the ones that were selected to perform duplicate detection, because those help sort of polarize the duplicate detection outputs more. And then we just took those duplicate groups, passed them through each of the submodels, unified the output structures, and then had a classification score for each image that was output. And we see that from this entire data set of images, the ones that have the highest classification scores have been highlighted in red in the on the right side. So our conclusion is that submodels help identify the specific features that we need for image culling. It makes it easier for the ensembling model to learn relevant information. And it's a strong approach, but there is still scope for comparison with newer models, particularly like vision transformers or SWIN transformers. And they may have very good performance in this task because they have the capability to pay more attention to certain parts of the image, which is kind of what we want to do. And we could also experiment by adding more submodels like maybe depth detection or pose estimation, because these are all things that wedding photographers may look out for when they classify images from weddings. And yep, that's the end of the presentation. I believe now we have questions.